fluids. So what this means is that the Tij is actually some constant, let us say capital C delta Ij plusCijkl, and then we had written del uk over del xl. Okay. So this is the definition of a Newtonian fluid. Okay. When we make the imposition that it has to be isotropic as well, in that case we can write thisCijkl as lambda 1 delta ij delta kl plus lambda 2 delta ik delta jl plus lambda 3 delta il delta jk. And we know this has to be equal to c jikl because tij is symmetric. So this whole expression has to be symmetric. The right hand side has to be symmetric in I and j. So swapping between I and j should not impact anything. So that means this should be equal to lambda 1 lambda delta ji delta kl plus lambda 2 delta jk delta il plus lambda 3 delta jl delta ik. And from here we saw that lambda 2 should be equal to lambda 3, right? And then we wrote this expression as, so we write Cijkl as lambda delta ij delta kl plus some mu times delta ik delta jl plus delta il delta jk, where I have written lambda 2 equal to lambda 3 equal to some mu. Okay, I have written it like that. And so now substituting this here, what do we get for Tij? So Tij, when we substitute here, so this term remains as it is. What about this term? When you multiply everything, so this becomes lambda delta Ij del uk over del xl times delta kl. Okay, lambda Ij del uk by del xl times delta kl. What is it going to be? What is this going to be? Del, del ukl, huh? Del uk by del xk or del ul by del xl, right? So this is simply going to be this plus mu times delta ik delta jl times del uk by del xl. So replace the indices, corresponding indices which you have in delta. So delta ik del uk by del xl is going to give you del ui, and then you're going to get del xj plus, what do we get here? Does someone recognize this? It is 2 times the symmetric part of velocity gradient tensor. Okay, so I can write this as C delta ij plus 2 Sij times mu plus lambda del ul over del xl times delta ij. What is del ul by del xl? That is the what is this del ul by del xl? Gradient? So what was the name that we gave? Divergence. This is the divergence of velocity. So this is basically the whole divergence del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3 times delta ij. Okay. So this is what we get for the stress tensor for a Newtonian and an isotropic fluid. Now when you have no flow, let us say the fluid is just stationary, there is no flow. Okay, there is absolutely no flow. Or let us say the fluid is moving as a rigid body with a uniform velocity, there is no gradient. Okay, there is no gradient in any direction, the velocity is not varying in space in any form. Then what do you expect for Tij to be? Is Tij going to be 0? Or what will Tij be when there is no flow, or let us say there is uniform flow in all directions? When you have uniform flow or no flow, which terms are going to drop out? Are all the terms going to drop out in Tij? So what will be left with? Tij will be equal to C capital delta Ij. So this C is the stress tensor in a fluid at rest. Okay, this C is the stress tensor in a fluid at rest. In a fluid at rest, let us say you have a gas or a liquid in a beaker or a container. What is the quantity that is exerting any kind of stress? In this room, let's say we do not ignore any, we do not consider any flow, then what is the quantity which is exerting some force on the walls in this room? Huh? Random motion of the particles, right? They are hitting the walls randomly, and there's a mean force or a mean momentum that they are imparting to the walls. Of course, there's equal momentum imparted from the other side, so they are not moving. But this is the specifically thermodynamic pressure. Okay, specifically this is the thermodynamic pressure when everything is at rest, but at finite temperature. We're not looking at things at 0 Kelvin. So when everything is at rest, then there is something happening in the fluid by virtue of which there is some stress. Now that stress has a very interesting property, and that is that this stress is isotropic, that is it is equal in all directions. Okay, so the convention is that we write this Tij at rest to be minus P delta Ij, where this is your thermodynamic pressure. Okay, this is your thermodynamic pressure, which is basically due to the random motion of molecules. Okay, so this is your Tij when you have a fluid at rest. Okay, so now substituting this in our expression, we write Tij to be minus P delta Ij plus 2 mu Sij plus lambda del UL by del XL times delta Ij. Now there is another pressure that I can define, and that pressure will include this thermodynamic pressure as well as whatever forces, whatever normal stresses that may be exerted due to the motion of the fluid. For example, let us say you have a fluid that is moving, and the motion is, how that motion occurs, let us not bother about that. Let me just ask you to accept that the motion is like this, that the fluid is moving with a velocity, let us say u1, and then after moving with u1, what is happening is that the fluid velocity is reducing. There is u2 which is less than u1. Okay, so if you look at the plot versus x, if you look at the graph of velocity, fluid velocity versus x, it's something like this. Okay, let us say this is a scenario. How that may occur is not of our business at the moment. Let us say this is happening. So in this case, what you can expect is that if you look at a fluid element, so imagine a fluid element that is passing through this flow. When it is passing through the uniform regime, the right wall of the fluid element and the left wall of the fluid element are moving at the same speed. So there is no deformation in the fluid element. But just when the fluid element reaches this zone where this is how the velocity looks, the right wall of the fluid element is moving slower than the left wall of the fluid element. So you would expect that as the fluid element passes through this region where velocity dips, the fluid element will get compressed. So there is a rate of compression that the fluid element experiences due to a sudden change in velocity. This type of change in velocity, the particular type of change in velocity here is the change in velocity in one direction, and the change is also in that direction only. So it is del u by del x. It is not del u by del y or del u by del z. It is del u by del x. Okay, it is the longitudinal derivative of the velocity. What that resulted here in is a compression of that fluid element. By nature of this compression, there is some stress that will be generated inside the fluid element, okay, or the rate of compression, there is some stress that will be generated inside the fluid element, and that will be basically the stress that is generated additional to the thermodynamic pressure of this fluid element. Okay. So, what we define is a mechanical pressure, and we write it as is the average of my longitudinal or normal stresses, that is it is equal to minus 1 by 3 T11 plus T22 plus T33. This minus sign is, I am including this minus signs to just subscribe to this convention that pressure is positive when it is compressive, that is it. Okay. So, when you look at it like this, so let us say we multiply this expression with delta ij, okay, because we want Tii. So, I multiply this expression with delta ij. So, Tij delta ij gives me Tii equals minus P delta ij plus 2 mu Sij delta ij plus lambda del UL over del XL delta ij. What is delta ij times delta ij? 3. So, we have Tii equals minus 3P plus Sij times delta ij, Sii, which is what? Divergence, which is this guy only. Okay. So, 2 mu, let us write it compactly like this because it is a scalar anyway. So, we do not care. So, Tii equals minus 3P plus 2 mu del dot U. What about this term delta ij times delta ij? Again 3 lambda del dot U, and Tii is simply minus 3 times Pm. Okay, which is the mechanical pressure that we have defined. So, mechanical pressure is equal to the thermodynamic pressure, at least in the special case when there is no motion. Okay, we will just see what are the other cases when this may be equal. So, we have, what do we get from this equation? We get that Pm, or let me take the Pm on this side. No, let me bring P on this side. So, P minus Pm equals, what do we get? 2 mu by 3 plus lambda times del dot U. No, this is the definition. I'm saying that in a general motion there is a general state of stress Tij, and I'm saying let me take an average of all the longitude normal stresses, and let me call that as normal mechanical pressure. Okay, let me call that as mechanical pressure, because in a general state of stress you would expect that the fluid element to be compressing or expanding due to whatever velocity gradients that you have in the motion. So, mechanical pressure is basically what would be the compressive pressure if the fluid was not particularly at rest. Thermodynamic pressure is what would be the compressive pressure if the fluid was at rest. Because that's how I defined Pm is Tii by 3. So, I need to take a contraction over Ij. The contraction means I need to replace J with I. हाँ कर लो, you can do that, you'll get the same expression. I just wanted to explain how you get that. Perfectly fine with that. Okay. So, P minus Pm is 2 mu by 3 plus lambda times this divergence of velocity. Now, if you recall, we had written the divergence of velocity as minus 1 by rho d rho by dt. We had said that divergence of velocity is directly related to the rate of change of volume. Okay. Divergence of velocity is directly related to the rate of change of volume. This quantity is also called dilatation in some literature. Okay. Basically, what is the divergence in velocity? It means how much compression or expansion a fluid element might be undergoing in the flow. Okay. And from the words that I am using, compression, expansion, it should be obvious to you that whenever we are discussing incompressible flows, this quantity would be 0, and that is what the continuity equation also gave us. When we are discussing incompressible flows, we are saying that the density cannot change, density of a fluid particle cannot change. That was our continuity equation, del dot u equals 0. So, in the particular case of incompressible flows, the mechanical pressure and the thermodynamic pressure are always equal. Okay. So, mechanical pressure del dot for incompressible flows which means mechanical pressure and thermodynamic pressure are always equal. What is the physical intuition behind this expression? What does this expression try to tell us? What it is trying to tell us is, let us imagine a cuboidal fluid element. Okay. Let us say you apply some pressure on that element. Okay. You try to change its volume. Okay. What it is trying, what this equation is trying to tell you is that when the fluid is being compressed, okay, the if you, let us say, keep the mechanical pressure constant, the thermodynamic pressure inside the fluid will be rising, and when the fluid has stopped compressing, that is when the thermodynamic pressure would be equal to the mechanical pressure. So, this is like an equilibration or a relaxation equation. What it is trying to tell you is, you have a fluid element, you start compressing it. Now, to compress it, you have to give a rate of change of volume. As you are compressing it, while it is being compressed, obviously mechanical pressure will have to dominate the thermodynamic pressure, only then it will compress. And what is trying to tell you is that it will relax, the thermodynamic pressure will relax to the mechanical pressure when the volume change approaches 0 gradually. Okay. What you can look at this equation as is, we have P minus Pm equals 2 mu by 3 plus lambda times that 1 by rho d rho by dt with a minus sign. Okay. So, if you keep Pm constant, this P will be adjusting as the rho is adjusting. Okay. So, you can think of it like a relation that is very similar to your equation of state, that how is the change in volume causing a change in pressure inside this fluid element. Okay. One important thing is that it is going to relax exponentially. So, I will give this as an exercise in one of your sheets, where I will ask you to calculate this term for an ideal gas, and let us see what you get, what is the result in a very cooked up type of an example. So, usually this 2 mu by 3 plus lambda is combined into a variable called kappa, which is called the coefficient of bulk viscosity. Bulk viscosity is very similar to what you have in solids as bulk modulus. Okay. What does bulk modulus do? What is the definition of bulk modulus? What is the definition of bulk modulus? Right. So, it is basically how much pressure has delta P by delta V by V. So, what is pressure, increase in pressure that has happened for a per unit change in volume. So, what this is trying to tell us is, what is the increase in pressure for a per unit rate of change of volume. Okay, because remember, this 1 by rho d rho by dt was equal to 1 by j dj by dt, where j was Jacobian. Okay. So, this gives you an intuition that this bulk viscosity, what is trying to do is, it is like a relaxation coefficient which is making the fluid element adjust to its surrounding pressure. Okay. If the bulk viscosity is 0, the fluid element adjusts to the surrounding pressure instantaneously. Okay. And that is what is known as the Stokes assumption. So the Navier-Stokes, why did Stokes get a credit? Is because he put in this assumption that I am going to assume that the fluid element relaxes to its surrounding pressure instantaneously, and I am going to say that this guy is 0. Unfortunately, he didn't know that he didn't have to make this assumption for incompressible flows. Okay, at that time everyone was trying to derive equations for incompressible flow, and even if he hadn't put that assumption, this guy del dot u is anyway 0, so things shouldn't matter. But what he said is, let's make this assumption of kappa equals 0, that means lambda equals minus 2 mu by 3, and this means that p equals pm always. So the moment you say kappa equals 0, you get p equals pm irrespective of it being an incompressible flow or not. Okay, the moment you say that I am working under Stokes assumption, you say that external pressure and thermodynamic pressure on a fluid element are going to be equal, no matter what is the nature of the flow, if it's compressible or incompressible, doesn't matter. Which one? So dilatation is the word that I am labeling this. This we got from the continuity equation. So within Stokes assumption, what does my Tij look like? So it is minus P delta Ij plus 2 mu Sij minus 2 mu by 3 del UL over del XL delta Ij. Now let us substitute this in our momentum equation and get our Navier-Stokes equation. So substituting this, main thing that we have to compute is del T Ij over del Xj, which is going to be minus P or minus del P over del Xj delta Ij plus 2 del by del Xj mu Sij minus 2 by 3 del by del Xj del U k over del xk del UL over del XL, whatever, doesn't matter. This is what we get. We can further simplify this. So this is basically minus del P over del Xi. This is 2 times del by del Xj. So let's write what this Sij is going to be. So this is mu times del Ui over del Xj plus del Uj over del Xi minus, there's a mu here, right? Yeah, minus 2 by 3 del by del Xj mu del Uk over del Xk delta Ij. So this becomes minus del P over del Xi plus del by del Xj mu del Ui over del Xj. Now here look at it carefully. This is plus del by del Xj mu del Uj over del Xi, and here we have minus 2 by 3 del by del Xj mu, I can write this del UK by del Xk. So this is basically del by del Xi because there is a delta Ij here. Okay. Now in this course we are going to work with constant viscosity. We are not going to work with fluids which may have a viscosity that is varying with velocity or temperature or other parameters. So for this course, mu you can assume to be constant almost always. If it is not constant, it will be specified and it will be a problem very specific to this part of our discussion. Okay, other than that, when we are discussing solutions of some particular scenarios, then mu is going to be constant. So in that case, our this term simplifies even more by del xi, and here we have mu times del 2 ui over del xj plus mu del xj del uj over del xi minus, so mu I can take common 2 by 3 mu 2 by 3 del xi. I can write del uk by del xk as del uj by del xj as well. And now here, as long as our velocities and their gradients are all continuous, I can swap the order of differentiation. I can write this term as del by del xi of del uj by del xj. Okay, I can do this. Okay, as long as the fields are continuous and differentiable, I can swap the orders of derivative. So this term and this term are basically the same. So the final simplification that you can get plus mu by 3 del by del x I del uj over del xj, which you can write in the direct notation that the stress tensor, or rather the divergence of the stress tensor, which is what we are looking at here, is actually equal to minus gradient of p plus mu. Now this is basically the Laplacian of velocity. Laplacian is defined, Laplacian of any quantity is defined as del dot of gradient. So it's the divergence of a gradient. Okay, you're taking divergence of a gradient for Laplacian. So this is what we have, plus mu by 3 gradient of del dot u. So this is just algebra. I just broke it down into steps so that you can get a revision of your index notation and everything. Nothing much fancy happening here. And now particularly for incompressible flows, we have del dot u equals 0, which means your del dot t term is simply minus gradient of p plus mu del square u. And substituting this in our momentum equation, we get the final version of our Navier-Stokes equation, which we are going to solve for different scenarios in this course, and that is del by del t of, so in the index notation if you write, it will be del by del xj rho u I uj equals fi minus del p over del xi plus mu del 2 ui del xj del xj. There is further simplification of this possible. There's further simplification of this possible, and that is, so I can break this down. So this is basically del rho by del t times ui, and if you break this derivative also down, you can write it as del by del xj of rho uj. Okay, you can write it like that as well, and then plus the remaining term, you have rho del ui over del t plus, so I took ui outside, now I take rho uj outside, and then rest is same. Now an important point that I want to make here is that This is where the incompressibility is playing a role so far. The left hand side, I have not made any simplification using incompressibility. Okay. I have never used any del dot u equals 0 in the left hand side of the equation. This is what you get when you apply Reynolds transport theorem. This is exactly what you get when you apply Reynolds transport theorem. There is no assumption of incompressible flow that I have made here, and I am going to keep it that way. I am not going to make any assumption of incompressible flow in the left hand side. Okay. So, the simplification, basically the simplification that I am showing you does not require incompressibility assumption, because if you look at this, for any type of flows, what is this? Del rho by del t plus del dot rho u, which is equal to what? This is what? No, no, no. This is what? Del rho by del t plus del dot of rho u. What is this equal to? This is capital D rho by dt. This should be 0. That is what continuity equation is. This is 0. That is what continuity equation is. So, this term actually cancels out and the left hand side simplifies to this, irrespective of me making any incompressibility assumption, irrespective of using del dot u equals 0. The left hand side has simplified to rho times del ui by del t plus uj del ui over del xj equals minus del p over del xi plus del 2 u mu del 2 ui over del xj plus fi. Now, the right hand side is very specific for my incompressible flow, but the left hand side, this term is not specific to incompressible flows. This is applicable for compressible flows as well, because I have not used the incompressibility assumption anywhere. Okay. So, as long as this continuity equation holds, as long as you are not adding mass and stuff like that in your flow, as long as there are no chemical reactions happening where you may have a right hand side source term on the continuity equation, there is no change in this term and this term is 0. So, this is what your left hand side simplifies to. The right hand side has simplified after incompressibility assumption, particularly this part. Okay. This simplification is due to incompressibility, which is what we did over here, this part. Now, what is this? Del ui by del t plus uj del ui by del xj. What is this? Hmm? This is the material derivative of velocity. What is that going to be? Acceleration. So, this is rho dui over dt equals minus del p over del xi plus mu, and this is your Navier-Stokes equation. If you ignore the force term, other forces like gravity and everything, then you will lose this Fi as well, and you will get an equation in velocity and pressure only, okay, without any force. So, usually, so in the direct notation, we will write this as rho du by dt equals minus grad p plus mu del square u plus this F, and usually this F will be called, which was the volumetric force. The other word written for this in literature would be body force. And as long as there are no electrostatic forces or gravitational forces or other type of forces, this body force will be 0. So, in your problems, exam problems or practice problems, if in the problem schematic I have not drawn a g vector, then you can ignore gravity and you can ignore this F. Okay, if I have not drawn this g vector, if I have drawn a g vector, that means that's a hint for you that please take gravity into account as well. LHS, I have not made an assumption. RHS, we have made a lot of assumptions. LHS is this for the general momentum equation. RHS, we have made a lot of assumptions. So this is Navier-Stokes equation for a Newtonian isotropic fluid in an incompressible flow. Okay, there are tons of assumptions here. It's for a Newtonian isotropic fluid which is undergoing an incompressible flow. Okay, for incompressible flow, what do we mean by incompressible flow for this course is that when del dot u is 0, that is when the density of a fluid element or a fluid particle is not changing. So let us quickly discuss the further part of our equation derivations and then we'll be through with this. After that, we'll just have to go through surface tension derivation and then we can close down our discussion on theory fundamentals of flows and then we can look at the maths of solving problems. Okay. So the remaining, I would say 2.5 modules are from this equation we are going to derive what is known as the kinetic energy equation, and then from the first law of thermodynamics we are going to derive the full energy equation and we are going to look at some interesting terms in them. And there was a hint of that term in your first quiz where we had that rate of work done where I had asked you to simplify that. Okay, so we'll see how that appears in our equations now. Any questions so far? Any conceptual doubts? So if you are not following each and every step of algebra, you feel it is going fast, too fast for you, or maybe some of you feel if it's going too slow for you, unfortunately this is my speed. Okay, so if it's going too fast for you, then no, make a checkpoint of conceptual steps that we have made. Okay, each and every detail of algebra you will be clear and confident with it only after you do this derivation yourself, only after you practice this thing. Okay, you follow this whole derivation and you literally take the next step in your derivation based on the previous step, trusting your previous step, and you follow this whole derivation yourself, only then you will be comfortable with it, with the algebra of it also. But at least the least you can do from the class is be comfortable with the conceptual steps that we have taken. So the conceptual steps so far are, so when in this equation we did not make any assumption. Okay, this is our momentum equation. When you apply Reynolds transport theorem, there's no modeling happening here. There's no modeling of this Tij. What is this Tij going to be? Okay, usually this process of estimating what is Tij in terms of velocity or velocity gradients, this is called constitutive modeling. I suppose you are doing this in multi-scale modeling course. I don't know. Have you been introduced to constitutive modeling? So in basically in multi-scale modeling or any type of modeling, constitutive model means how do you relate the microscopic properties of any matter to the macroscopic variables. Eventually everything is solving F equals ma at the molecular level. I mean, assuming classical mechanics, every molecule is undergoing F equals ma, where F is due to the intermolecular interactions and so forth. Okay, but how do you relate, how do you scale that behavior up to the human scales, human level scales, not angstroms or nanometers, to millimeter, meter, centimeter scales? How do you do that? So this information of atomistic behavior to the macroscopic behavior is called constitutive modeling, and we literally just bypass that in one equation by saying that this Tij is proportional to velocity gradient. That is the constitutive modeling step. Once I made that assumption and made the other assumptions of isotropic fluid, then the expression of Tij was derived. Okay, so that step of constitutive modeling, you are definitely not expected to know how that comes from. That is someone's intuition over years of working, and they put it down in an equation. They are not supposed to understand at this level how that comes. Okay. But after that assumption, you are supposed to be comfortable with all the algebra and concepts. That once I have said T is proportional to velocity gradient, how does everything else follow? Okay. All of this derivation, by the way, is given in all of the reference textbooks as well, in Panton, in Kundu, in Aris. All of these textbooks cover these derivations thoroughly. So, before we move to the total energy equation, let us derive the kinetic energy equation. Okay. And to do that, what I am going to do is, I am going to take a dot product of this equation, or maybe not even this equation. Let us derive the kinetic energy equation from this. So, I am going to write this with the left hand side simplified like this. So, I am going to write this equation, and that is rho times del ui by del t plus uj del ui over del xj equals fi plus del tij over del xj. And what I am going to do is, I am going to multiply this equation with ui. So, this is very important. This was the ith component of a vector equation. Maybe I did not specify this explicitly. This is a vector equation. These are three scalars equation. Okay, I equal to 1, I equal to 2, I equal to 3. These are three scalars equation. So, I have multiplied the ith component with the ith component. So, essentially what I am doing here is, I am taking the dot product of the momentum equation with velocity. I am taking the dot product of momentum equation with velocity. Okay. So, let us consider this dot product. Look at this. What does this expression give you? So, this is rho ui del ui by del t, which you can write as rho del by del t ui by 2. Okay. Which I am going to write as is rho del by del t of u square by 2. Okay. So, u is basically mod of or magnitude of velocity vector. Okay, u is the speed. Look at this term. This is ui uj del ui by del xj. This I can write, okay, rho is also there. So, I can write this as rho uj del by del xj of again ui by 2, which is rho u dot grad of u square by 2. And then the right hand side is, so we have ui fi, which is nothing but u dot f, and then we have ui del tij by del xj, which is nothing but u dot del dot t. Maybe write it like this. The meaning of each of these will become clear in a moment. Meaning of each of these will become clear in a moment. And when we put them together, what do we get? Rho times del u square by 2 by del t plus u dot grad of u square by 2 equals u dot f plus the cumbersome expression this. Okay. Now, you can apply the reverse of this step here. Okay. This step is what? This expression is what? This is rho times del u square by 2 by del t plus rho u dot grad of u square by 2. What I can do is I can add to this term a u square by 2 times the continuity equation, and this is a very standard trick in a lot of fluid mechanics when we convert these governing equations in one form to the other form. Okay. These forms I will specify when we look at the energy equation. There is a specific word to these forms, and when you are keeping the rho outside the derivatives or inside the derivatives, that is how you can think of it right now. What I am doing is I am adding to this expression, which is simplified to this term. Now this term is 0. So I am adding a 0 on the left hand side, so it should not matter. But after adding this, the derivatives actually simplify. Okay, all the derivatives combine together, because this term becomes rho del u square by del t, del by del t of u square by 2, and here you have u square by 2 del rho by del t. So you get del by del t of rho u square by 2, and here we have a del dot rho u times u square by 2. Here we have a rho u dot del u square by 2, that becomes del dot of rho u square by 2. Okay, that becomes del dot of rho u square by 2, and this rho u square by 2 is by definition our kinetic energy density, or particularly kinetic energy per unit volume. So we have derived, using the momentum equation, we have derived the so called kinetic energy equation. So we have del by del t of, let me write this u square by 2 as a variable k. So we have rho k plus del dot of rho uk equals u dot f plus u dot del dot t. Now let us try to physically visualize what the right hand side terms are. So the left hand side should be very straightforward for you. It is the rate of change of the kinetic energy inside a fluid blob. Okay, you can visualize this as the application of Reynolds transport theorem. So if I integrate this thing over a fluid blob, then you can visualize the left hand side as d by dt of rho k dv. Okay, you can go reverse in the Reynolds transport theorem, and you can replace this by this. So it is the net rate of change of the total kinetic energy of a fluid blob. And what is it equal to? What is this u dot f? It's the rate of work done by volumetric forces or body forces. That's what u dot f is, right? It's the rate of work done or power of the volumetric forces. And what is this u dot gradient del dot t? So the way you should visualize this as is u dot del dot t, where del dot t is a type of force or a mechanical force. So when I say a mechanical force, what I mean is, by virtue of this force, by virtue of del dot t, there is going to be some movement of the fluid particle. Why? So let us say this is your fluid particle. Of course, this is not a fluid particle, but let us say this is a fluid particle, and I am applying some stress here, and I am applying a different stress here. Okay. Let us say I am compressing it with some strength here, but I am not compressing it with equal strength here. As a result of that, there is some residual force which is going to cause motion of this. So the divergence of stresses give you the net imbalance, which creates an external moving force on the fluid elements. So del dot t is giving you, so del dot t in one direction is giving you the net force that is on the center of mass in one direction, and u dot del dot t is the rate of work done due to that force. Where did I keep the mark? Anyways, we are quite near the end of this lecture. So this u dot del dot t is the rate of mechanical work done. Okay, this u dot del dot t is the rate of mechanical work done. Whenever I say mechanical force, mechanical work done, these things are making the fluid elements move. They are not going to deform the fluid elements. Okay, they are making them move as a rigid body. There is a net force on the center of mass and making them move as a rigid body. In our next class, we'll look at the total energy equation and we'll separate out the rate of deformation work done as well.